Assalamualaikum and good evening. I am Muhamad Haikal Izzuddin Rohaimi alongside my fellow supervisors Izzat Anwar, Azhan Abdul Aziz and Iriani Abdul Halim Chu from Department of Built Environment Studies and Technology, UiTM Sri Iskandar Perak, presenting to you our research title Comparative Thermal Performance of Stilted and Terrestrial Riverside Village Stay Buildings under Tropical Climate Conditions. The contents of the presentation follows the standard research trajectory, moving from the introduction to the research gap, aim and objective, to the literature review, the methodology, and a deep dive into the result areas and discussion, and finally to the conclusion. We start our introduction with a paradox named the unsustainable sustainable. When we think about it, globally and also in the ASEAN region, tourism development has increasingly shifted toward a more sustainable tourism models, which include community-based tourism, ecotourism, and also rural agrotourism, which all these emphasize on the environmental experience and local context. In tropical regions, specifically in this research area, many village stay facilities are located along riverbanks are essentially intended to benefit from natural landscapes and microclimatic potential. However, being in these tropical regions, thermal comfort is always a persistent challenge. Despite the eco-friendly branding introduced earlier, the building sector accounts for a substantial share of energy use, which cooling demand forming a major portion in warm regions. Therefore, many small-scale tourism buildings rely heavily on mechanical cooling such as air conditioning. From this, we can essentially see that a mismatch between the sustainability objectives and also the operational practice reality. In conjunction with the previous slides, we can clearly see the intent contradiction. How about we looking back at our vernacular tropical architecture where passive environmental control can be achieved through climate responsive design. Traditional Malay stilt houses, which is the elevated one, incorporate elevated floors, lightweight materials and permeable building envelopes to enhance ventilation and reduce heat accumulation. Settlements also benefit from proximity to water bodies, which can reduce surrounding air temperature when building form and layout allow effective airflow penetration. Okay, this principle suggests that building morphology and elevation play a critical role in passive cooling performance. Alternately, many contemporary village stay and homestay buildings, including our very own kampung today, adopts enclosed layout, which is for the air conditioning, and heat retentive materials such as metal roofing without adequate passive design strategies. Poor ventilation and inappropriate envelope configuration have been shown to increase indoor heat gain and occupant discomfort. Today, homestay buildings, even in riverside location, cooling benefits are often reduced by improper building density and the orientation that obstruct airflow from the water body. Okay, although passive cooling strategies are widely discussed in the previous literature, their application in current tourism facilities specifically is often fragmented and lack performance-based validation. The research gap is limited availability of field-based quantitative comparisons of passive cooling performance between different riverside building typologies. As mentioned in the previous slide, most previous studies emphasize only the general guidelines or simulations. However, a measured environmental performance data that compares terrestrial and stilted village stay buildings in the actual tropical condition is still limited. Therefore comes the research aim to quantify and compare the passive cooling performance of terrestrial and stilted riverside village stay buildings typologies under tropical climate conditions through on-site environmental measurement. So how is the on-site environmental measurements? Through the objective to evaluate cooling efficiency and airflow behavior in order to provide empirical evidence that support climate responsive design strategies for a low energy riverside building facility. Moving into the literature review, respond to the intent contradiction from the earlier slide. This brings us back to passive. First, regarding the thermal comfort, as the study aims to quantify empirical studies and evidence, this research used ASHRAE benchmark to define success. Note that wind speed between 9 to 15 km per hour are essential for good passive cooling in these environments. For the tropical climate condition, Malaysia context, in the Malaysia context, we face constant high humidity and temperatures averaging 23 to 32 degrees Celsius. Here, passive design is not just an option. It requires low thermal mass envelopes that allow heat to escape continuously rather than trapping it. So for the passive cooling strategies, our passive cooling strategies focus on reducing mechanical reliance by considering orientation and shading in the early design phase. We can significantly reduce the carbon footprint of these tourism facilities. For number 4, building orientation, layout, and openings is focused on the porosity. We have found that wall-like linear buildings actually block river breezes. Instead, we advocate for clustered, permeable layouts that preserve ventilation corridors, ensuring that natural cooling reach every occupied spaces of the tourism facilities. Building on the gaps identified in the literature, we move to our methodology. To validate these theories, we conducted field-based quantitative comparisons between two distinct architectural typologies. For the case study 1, case study a linear water-dwelling typology that maximizes exposure but risks wind shadows, and case study B, a clustered, compact riverside typology integrate with vegetation to moderate the microclimate. By comparing these, we can isolate how morphology and elevation directly impact airflow friction, temperature difference, and also thermal comfort. So for the instrumentation and protocol, for the data, we utilize handheld digital anemometers to measure air temperature, wind speed, and direction across various spatial zones. So our protocol ensured reliability by measuring only during stable sunny days to capture the full daytime thermal cycle. This allows us to calculate cooling efficiency using temperature differential, providing empirical proof of passive performance. Moving into our results, we first examine the morphological impact on microclimatic response. Our architectural analysis highlights a fundamental divergence in how each facility engages with the riverside. As seen on the side plan, case study A adopts a dispersed terrestrial layout with some of the units set back from the water, while case study B utilizes a clustered amphibious typology with structures built on stilt directly over the water. So the findings win the performance. The results stuck in case study A, the linear arrangement and dense vegetation actually create a wind shadow, dropping average wind speeds to just 3 to 6 km per hour. However, case study B achieves speeds of 9 to 12 km per hour. This confirms that the stilted form is superior. It reduces surface friction and allows unobstructed airflow beneath the floor plate, utilizing the cooler river surface to precondition the air before it enters the occupied zones. Essentially, Table 5 proved that a compact elevated morphology outperformed dispersed terrestrial layout in harvesting natural cooling. Next, we look at thermal performance and cooling efficiency, where our quantitative data reveals a stark contrast. Efficiency was calculated based on the temperature differential between indoor and outdoor environment as seen in the graph on the right. The performance patterns vary significantly across the different spatial types and times of the day. So, case study A demonstrated a critical thermal failures, particularly in the morning. The public facility recorded a negative cooling efficiency of negative 11.54% at 8 a.m. This indicates a heat trap condition where the building envelope retained solar heat from the previous day. Despite deep roof overhang, the lack of high-level ventilation prevented buoyant hot air from escaping, creating pockets of stagnant heat for the case study A. And for the case study B, consistently achieve positive cooling efficiency, peaking at approximately 11%. Indoor temperature remains stable and significantly lower than the outdoor ambient during peak afternoon hours, even during the evening. The success is attributed to the stilted, breathable roof design and low sill heights, ranging from 0 to 0.4 meters, which facilitate continuous stack ventilation and enhance cross airflow. We now look at the aerodynamic porosity, which our analysis identified as the primary driver of ventilation success. Although both case study sites share the same regional wind baseline of approximately 13.5 km per hour, their internal wind environments told two very different stories based on the architectural factors. Case study A, velocity drop averaging only 4.9 km per hour as shown in the wind roses figure. The terrestrial layout and the dense vegetation act as windbreaks, reducing wind speed by over 60% as air moves from the exterior toward the interior spaces. Meanwhile, for the case study B, the stilted clustered typology recorded wind speeds that effectively match the regional baseline, the 13 km per hour. The column-only structure and full-height openings create a low-resistance profile. This allowed the venturi effect to accelerate airflow through the clusters. This challenged the conventional assumption that lower density equates to better ventilation, as suggested in the previous literature. Instead, uh, Instead, the results suggest that the clustered streamline morphology as seen in case study B create wind tunnel effect that effectively channel cooling breezes, whereas dispersed but obstructed layouts in the case study A dissipate wind energy. Moving to our final findings on environmental synergies, we found that proximity to water is far more critical than its total area. Case study A has massive aquaculture ponds, but because they are disconnected from the building footprint, they provide negligible cooling. In contrast, case study B's tilted positioning over the river creates an active cooling corridor where air is pre-cooled over the water surface before entering the envelope. We also observe species-dependent vegetation effects. Case study B used a high canopy content wood tree to shade the roof while keeping the window at ground level open for maximum airflow, while the tree acts as shading device for the overall scheme. So synthesizing these results, we established three design imperatives for riverside tourism. First, terrestrial setbacks are climatically inefficient. Buildings should be elevated on stilt to minimize surface friction. Second, thermal traps are caused primarily by stagnant air rather than solar gain alone. Finally, we must prioritize permeability over insulation, specifically in the riverside area, by using full height openings and ventilated roof ridges. Together, these strategies allow buildings to revert to a naturally ventilated, amphibious morphology that responds directly to the tropical hydrological context, which is the riverside itself. In conclusion, our research established a definitive link between architectural typology and thermal success. We have demonstrated that the performance of riverside village stays is fundamentally dictated by typological choice, showing a stark contrast between traditional stilted forms and modern terrestrial layouts. While grounded terrestrial facilities often suffers from a heat trap effect, which with a negative cooling efficiencies as low as negative 11.54%, stilted amphibious structures maintain a consistent positive efficiency of approximately 11%. This disparity is driven by the stilted configuration's ability to harvest natural river breezes at speed of up to 13.7 km per hour, which match the regional baseline, whereas terrestrial buildings act as aerodynamic barriers. Ultimately, for long-term sustainability in tropical tourism, designers must prioritize morphological breathability over energy-intensive mechanical systems. By returning to core principles of permeability, altitude, and environmental synergy, we can create an authentic low-carbon experiences that are naturally attuned to the tropical climate, which conclude that passive cooling is the actual technology from the ancient times that is evergreen, relevant to our context, and in this case, to the tropical climate riverside. So that's all from me. Thank you.